Two capacitors have capacitances 6 microfarads and 9 microfarads. They're connected in parallel, and the resulting combination is attached to a 9-volt battery. Let's draw the setup. Okay, so first of all, let's go ahead and draw these capacitors in parallel. In a circuit diagram, capacitors are drawn as just single lines that are parallel with each other, and each of them represents one plate of the capacitor. Now, since we have two capacitors in parallel, we need to draw two parallel branches, each one of them having a capacitor of its own. And now we want to attach them to a battery. This will be the positive side of our battery, and this will be the negative side. To connect them in parallel, we would connect our positive terminal to one end of the first capacitor's branch, but then we also need to connect to the second capacitor's branch as well. And then we want to do the same thing with the negative side. This is an example of capacitors in parallel. All right, so let's analyze the potential at different points in this diagram. Now, according to the givens, we need a 9-volt battery. By convention, we're going to label the negative terminal of that battery 0 volts. And we're going to label the positive terminal of the battery 9 volts. Now, parts of a conductor that are in contact with each other are going to have the same potential as long as there's equilibrium. So all of these points are at 9 volts of potential. However, on the other side, we see that all of these points in contact are going to be at 0 volts. What this tells us is that there's a 9-volt potential difference across both of the capacitor gaps, and that's significant here. Let's find the equivalent capacitance of the combination. Now remember, we do have a formula for capacitance. It's A epsilon naught over D. That's the one we want to use here. Alright, so one of these capacitors is a 6 microfarad capacitor, and the other one is a 9 microfarad capacitor. And remember that the capacitance tells us about its ability to hold charge under a given potential difference. Now we see that the potential difference across both of these capacitors is actually the same. Okay, so one of them is going to be able to hold more charge. And that's what the battery is going to do, is it's going to push charge onto the plates. The 9 microfarad will hold more. So we expect to see more negatives on this side than we see on the 6 microfarad capacitor below. Capacitors will attract an equal amount of charge on both sides. Now notice that both of these devices are attracting charge. If we wanted, we could redraw the situation such that both the capacitors C1 and C2 were combined into one large capacitor with a greater capacitance. It's called an equivalent capacitor, and it will have the symbol CEQ, where the EQ stands for equivalent capacitor. This is a technique for analyzing and solving complex circuit problems where there's more than one capacitor involved. The formula that we'll use for this will be that the equivalent capacitance of the big capacitor will be the sum of the two original capacitors. Now this is only valid when we're using capacitors in parallel. And we'll see in the future that there are other rules for other situations. But anyway, the amount of charge that CEQ can hold will actually equal the sum of the charges that the two of them would have held in our other diagram. So it's going to be a lot of charge. And in fact, the rule for this will be that the Q total will be the sum of the Q on each of the individual capacitors. Alright, so what does our equivalent capacitance become? Well, we have to add 9 microfarads plus 6 microfarads. Add the 6 microfarad capacitance plus the 9 microfarad capacitance. And we find that the total capacitance then will be 15 microfarads. This is the answer to the first question of this page, which said, what was the equivalent capacitance of the combination? It is 15 microfarads. Now, we're asked, what is the potential difference across the capacitor? Well, before, the potential difference was 9 volts for C1 and 9 volts for C2. If we look at our equivalent drawing, we can see some similarities. One similarity is our positive terminal is at 9 volts, and since the left plate of our capacitor is in direct contact through a conductor to that point, it's also going to be at 9 volts. Over here we've got 0 volts at the negative terminal, and our negative plate is in direct contact with that, so the negative plate's going to be at 0 volts. So once again, the delta V across that gap is still 9 volts. And that's something we're going to see with capacitors. The delta V of the equivalent capacitor will equal the delta V of the first, and it will equal the delta V of the second capacitor as well. They'll share the same delta V. So, the answer to this is 9 volts. Now we'd like to find the charge stored on each capacitor. For this, we can use the rule C equals Q over delta V. We can rearrange it and solve for Q, and we'll get this. Now if we apply it to capacitor 1, we'll get 6 microfarads times 9 volts. That's going to be 54 microcoulombs. And that 54 microcoulombs is going to be on this C1. We'll have a positive 54 microcoulombs here on the positive side. We'll have a negative 54 microcoulombs. Alright, now we want to apply that to capacitor 2. And let's see, we're going to get 9 microfarads times 9 volts, 81 microcoulombs. So just as we suspected, capacitor C2 can hold much more charge. Plus 81 microcoulombs on the positive plate, negative 81 microcoulombs on the negative plate. The last question says, how much total charge leaves the negative terminal of the battery? So one thing we see in these situations is we have to have conservation of charge, which means that charges can't be created nor destroyed. So when they leave the battery, they have to decide which path they're going to take. So are the charges going to go up to capacitor number 2, or will they take this route and go to capacitor number 1? They can't go to both, so they're going to have to pick one or the other. And what will happen here is an amount Q total will leave the battery. Okay? But Q1 will appear on capacitor 1, and Q2 will appear on capacitor 2. Okay, so we're going to have Q total will equal Q1 plus Q2. Now in this problem, I'm just going to look at the magnitude of the charges. I won't worry about the sign of it. So what we're going to have here is so we see that 54 microcoulombs of negative charge piles onto C1, and 81 microcoulombs of negative charge piles onto the negative plate of C2. We want to add those together to figure out how much total charge is leaving the negative terminal. It's going to be 136 microcoulombs. Now in our diagram that we drew, we said that Q total would pile onto the plates of this imaginary equivalent capacitor. So that means we'll expect to see negative 136 microcoulombs on the negative plate, and we'll see positive 136 microcoulombs on the positive plate. In both of these cases, the amount of charge that leaves the battery is Q total, which is 136 microcoulombs of negative charge. The only difference is that in this case, what we have is called a simplified equivalent circuit. We'll see how it's useful in the future.